I am here to tell you about the MicroFluigis project, and what this project is about is it is going to harness the power of the FPGA and bring that into the microfluidic domain with the ultimate goal of bringing a functionality to a chip that currently does not exist, whereby we can query the device, the actual chip, for its current state and make decisions like open and close valves based on the current state of the fluids inside of the chip. In order to do that, we segmented the project into two independent thrusts. The first thrust is to create a user-friendly dynamic reconfiguration environment. Dynamic reconfiguration exists to program a chip and then reprogram a portion of the chip without interrupting computation in the unaffected portions of the FPGA. The parallel processing aspect of this project reads from multiple sensors in parallel, interprets the results, and presents them in human-readable form. So first, I will talk about the dynamic reconfiguration piece. And what dynamic reconfiguration is it differs from partial reconfiguration in that in partial reconfiguration, the chip is initially programmed for some function and computation is started. That computation is then paused in order to reprogram a portion of the chip. Once that portion of the chip has been reprogrammed, all computation is resumed. How dynamic reconfiguration differs from partial reconfiguration is that in dynamic reconfiguration, the chip is initially programmed and computation is begun, but the portion of the chip that is reconfigured does so without interrupting the computational aspects of the chip that is not being reconfigured. Once the portion of the chip has been reconfigured, it begins executing computations. There are two main terminologies you need to know for dynamic reconfiguration, the first of which is a reconfigurable partition. A reconfigurable partition is like a space saver inside of your static logic. Static logic is, as it sounds, the portion of the logic, the portion of the FPGA that does not get reconfigured. Inside of these reconfigurable partitions, you can have many different types of reconfigurable modules. Each reconfigurable module fits perfectly inside of its reconfigurable partition. Now, this slide is meant to show that the difference in synthesis process, that is Verilog to bitstream, is significantly different for a reconfigurable design when compared to a traditional design. In a reconfigurable design, synthesis is performed out of context. What that means is that each reconfigurable module must be synthesized independently of the static logic, and a netlist must be generated for each reconfigurable module. Design rule checks must ensure that each possible design functions within the user's constraints. Now, in order to do this, there is no nice GUI double-click button that will do dynamic reconfiguration. So what this project attempts to do is it attempts to set up a project as you would in the ISE GUI and run a tool command language script that will perform all synthesis to bitstream, perform the entire process of going from Verilog to bitstream. All of the tool command language scripts are segmented by functionality. Bottom line in this slide is that there are many things that must go on under the hood. The same way that in ISE, programming a FPGA takes a lot of under the hood knowledge in order for it to work. Unfortunately, for dynamic reconfiguration, all of this complexity is presented to the engineer, until now. In this project, the engineer is only responsible for modifying the top tool command language or TCL script called design.tcl. Inside of the script, you would set up a project similar to how you would set up an ISE project. For example, in order to define your target hardware device, what you would do is you would select your device, package, and speed grade similar to the ISE GUI. The only difference is you're having to type in the device, package, and speed grade instead of select it from a drop-down menu. This is just a portion of the functionality associated with the top-level script. How to set up the entire script to execute your project is very well documented in the designs README. In order to execute this script, one must simply just execute 2 lines on the command line. You would start Vivado in TCL mode and source the design.tcl file that you saved for your design. After which, the tool command language scripts will take over and your bit streams will be generated automatically. And this concludes the dynamic reconfiguration portion of the project. For parallel processing, the goal is to read from many different types of sensors and interpret and present those sensors in human readable form on an LCD. In order to do this, each sensor would have an associated Verilog file associated with it. All of these sensors would be tied together into an interface and presented on an LCD. You can have as many different types of sensors as you have space on your FPGA, and obviously as you have sensors. You may also duplicate sensors. In this example, there is a color, a pH, and a light intensity sensor, but it is also feasible to have 3 color sensors. For the demo, what we did was we have 2 color sensors. Actually, we have 2 color sensors talking to the FPGA, and the results are being displayed on an LCD. Also, the FPGA can issue commands to the color sensors, such as enter one read-only mode and continuous read mode through the use of the dip switches associated with the Basis 3 board. In this demo, we have a single color sensor attached to an LCD, the data being interpreted by an FPGA. To take a single reading, you flip a dip switch, which will take a reading from the color sensor in RGB form. Flipping another dip switch puts the sensor into continuous read mode, where it will continuously probe for RGB values. Covering the probe shows that the RGB values go to 0.